Hi everyone, as always we start with the learning objectives in here, and as always they will be repeated at the end, and please feel free to ignore these and take a look at them at the end. First of all, let me apologize for bringing your hopes up. We're not going to talk about cars that turn into robots that kill people. Sorry. A transformer is something a little bit less exciting for, engineers get really excited. And the idea is that we have something like this, and this is an iron core, and then you add some wire going around it, because remember we always like to add wire that goes around things, and then we connect this to a power supply. And the idea is that, well, this for the moment is an electromagnet. We will get into what a transformer is in a second. So remember that when we have something like this and we turn it on, then this creates a magnetic field. Let's add a little switch here. So here's a little switch that will allow us to turn this on and off. And let's say that I'm not happy with this, and I add another piece of wire here. So here's another piece of wire that I coil around. And here's an ammeter, which remember measures amperes. And now when this thing is open, there's no current here, this is just a piece of iron, and this measures absolutely no current because, there's no power source. So of course there's no current. Now, what happens when I turn this on? Well, when I turn this on, this suddenly generates a magnetic field, which means that there is a change in the magnetic field that this thing sees. And because there is a change in the magnetic field, remember that there's all these new field lines that are going across this thing. And if you remember anything about induction, you will remember that that's exactly what caused an EMF. So turning this on will cause a change in the magnetic field that goes through this, which will cause an EMF, which will cause a current. And then I will be able to measure a current going through here. The problem is that once this is on, and the magnetic field has been established, then finally all the electrons will stop moving until they're all happy with their location and the current will stop. So if I want the current to continue, what I would have to do is to turn this on, off, on, off, on, off. And this would keep creating a current every time that I turn this off. Because remember, an EMF is only created when there is a change in magnetic field. So once the magnetic field is established, the change stops. So this gives us an idea, right? Wouldn't it be nice if we could have some kind of current here that's always changing, so that this is always changing, and this would generate here a current that's also always changing. So I could, without touching, I could transmit energy from here to here. Wouldn't that be cool? Well, you may not think that's cool, but lots of people thought that was very cool, and that's basically what a transformer is. So what we can do is say, well, okay, how about instead of using this type of power source, I use an alternate power source. And remember, we did that the other day. We talked about AC power. So instead of this, what we use is an AC source, which means that our current is really going this, 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 this. So the magnetic field that this thing is created is continuously changing. First it points this way, then this way, then this way, then this way, then this way. And therefore, this is seeing a change all the time. And this creates also an alternate current here that goes this way, this way, this way, this way, this way. So basically we can replicate the current going on here in this other coil. So we found a way of transmitting current from one place to the other without touching, and that's really cool. But it gets better. Now, this is a very rudimentary way of transmitting current, and the really, really cool way is this. So what you do is, instead of one iron core, you get something like this. So let me draw this. You get, so all of this is iron. Okay? And now what I do is I wire my AC supply here. So, and this goes like this, like this, like this. Okay? And I'm going to call this thing here my primary or my input coil. Okay, and this is going to be called my primary or my input voltage, because we have a voltage that's being supplied. Input voltage. And then I'm going to make another coil here. So first thing, let's just say that this has, let's just say, I don't know, 10 coils. Sorry, 10 turns. So this coil has 10 turns. Actually, if you count them, this last, but let's imagine it has 10. Now I can do the same in this branch here. So I'm going to, again, get some wire and coil it around. And the beauty of this is that I don't have to use the same number of coils. I can use a different number of coils, and that's what makes the transformer so cool. That's why it's called a transformer, because it transforms what I input into what I output. So I'm going to call this thing here my secondary or my output coil. And of course, this is going to be my secondary, come on, you guess this one, or my output, what? Voltage, exactly, my output voltage. Okay, and let's say that this thing has, I don't know, 20 turns. And again, there's less than 20 turns if you look at it, but we're just imagining things because, you know, we're a little weird. So now I have this thing, and what my iron core does is it makes sure that no magnetic field escapes. So the thing about, remember, iron is that when there's a magnetic field in it, it gets magnetized very easily. And it does not let the magnetic field lines escape into the air, which means that all the power that I'm giving this thing will go through the magnetic field lines into this one, and no power will be lost. When you design a transformer properly, you can get up to 99% efficiency. So this thing is really efficiency. You almost lose no power going from here to here if you use a proper core. And this is normally an iron core, and normally it's laminated to avoid something called eddy currents, but you don't need to know that. All you need to know is magnetic field is confined here, cannot get out, and therefore no energy is lost to the surroundings. Okay? And now we ask ourselves, okay, so what happens when I have a certain primary voltage here? Then this is constantly changing, so it creates a constantly changing magnetic field that goes around like this, right? And this magnetic field now goes into here, it keeps constantly changing, so it creates a secondary output. So here it's as if there was a generator, but actually the generator is just this thing being transmitted to the magnetic field. And now what I ask myself is, okay, so this changing EMF, because there's all these different currents, will create a magnetic field. But here I have 10 turns and here I have 20 turns, which means that there will be more magnetic field lines crossing this than there are crossing this. In fact, there will be twice as many, because here I have 10, here I have 20. So for each magnetic field line that comes out of here, I will have 2 crossing this, because remember, this crosses 1, 2, 3, 4, 5, 20 turns. So ask yourself this, should I expect to have higher voltage here or here? And if higher, how much higher? Pause the video and give me some kind of answer. Okay, hopefully you did this and you realize that because there's more turns here, then there's more magnetic field lines crossing this, and because the more magnetic field lines, the more EMF, I should have more EMF here. In fact, because there's twice as many field lines crossing this, I should have twice as much EMF here and here. So not only I found a way to transmit electrical power, I actually found a way of making it bigger. So the power that goes through here, not really the power, the EMF that is supplied here, I can multiply it by 2 simply by having 10 turns here and 20 turns here. And in general, if I have 10 turns here and 50 turns here, then I will have 5 times the EMF. And if I have 5 turns here and 500 turns here, then I will have 100 times the EMF. I will always have as many times the EMF here as many turns I have here than here. So we can put this into an equation. Let me show you the equation. So the idea is that if I want to know the ratio between the input voltage and the output voltage, so let's just call it voltage output over the voltage input, that really depends on the number of turns that I have here and here. And remember, the more turns I have here, the higher this is going to be. So this is going to be up. So the number of turns in my output divided by my number of turns in the input. Which means that if I have 100 times more turns here than here, then I will have 100 times more voltage here than here. If, on the contrary, I have less turns here than here, then I will have less voltage here than here, and so on. So I can use this thing to increase my voltage, decrease my voltage, do whatever I want with my voltage with hardly any losses. And if you were an engineer, you would be very excited. Now, by what I just told you, it may look as if I can create free energy, right? Because this thing has an EMF, this thing has another EMF, and I can actually multiply by EMF by like 100. So this is like having 100 more batteries, right? So this thing should have more energy than this one, and therefore I can use this to create free energy. Now, if you know anything about energy, you are probably aware that this is not possible. So there must be some kind of catch. And indeed, there is a catch. And the catch is the power equation. Now remember, hopefully you remember this from electricity, that we can calculate the power supplied by something by multiplying the voltage, or the PD, times the current. And if you don't remember this, remember that the power was like the brightness of a bulb, right? So the more batteries, remember that the voltage is kind of the amount of batteries, the more batteries, the more power. And the more current, the more things that are going through the bulb, also the brighter it is, right? So the more batteries, the more brightness, the more things that are going through the bulb, the more brightness. Okay, so we have this thing here. So what happens is that really I can't create energy. So the power that I supply this thing has to be exactly equal to the power that I supply this thing. So if the power here is 50 watts, the power here is also 50 watts. And if this is 200 watts, then the power here is also 200 watts. So what I'm changing really is this part. But what I'm not changing is this. So what I'm really saying is that the power at the input has to be equal to the power at the output. And let's see what that means. Okay, so, well, let's write that out. So the power at the input is just the input voltage times the input current. And that has to be equal to the power at the output, which is this one, which will be equal to, you tell me. Yes, the output voltage times the output current. So this has to be equal to the output voltage times the output current. And this is basically the equation that we need to remember. And what does that tell us? Well, this tells us that if I make this way bigger than this, then this will be way smaller than this. So when I increase the voltage a lot, then I have to decrease the current a lot, so that these two together still give me the same power that I had at the beginning. If I decrease the voltage a lot, then the current is going to increase a lot. So every time that I use a transformer to increase the voltage, I'm decreasing the current. Every time that I use it to decrease the voltage, I'm increasing the current. And this may look like a problem, but this is actually very, very, very handy because of this. Now, imagine that I have a factory that makes electricity. So I have a generator. So here's my generator, that makes electricity, and I have to send it across the country. So this means I have to connect this to my electricity poles. I have these cables, and these cables are very, very, very long. So they'll have a certain resistance. Now remember, hopefully you remember this, but if you don't, that the fact that this equals IV, and because V equals IR, then the power dissipated at a certain resistance is I square R. And you're saying, okay, so what? Well, so this. If we have very low voltage going through here, because of this, we have very high current going through here. If we have very high current going through here, do you see the power is proportional to the square of the current? That's the power lost at the wire. And we have kilometers of wires, which means that if we are transmitting electricity with very low voltage, we will have really high current. There will be huge power losses at the wire, which means that all this energy and money that I'm spending on my factory to create this current is being wasted because the wires are overheating and losing all this power. So that's not cool. So what would I do if I was a guy that has an electricity generator and wants to sell his electricity? Well, what I would do is make sure that this current is as small as possible. And how can I do this? Well, again, using this, if I make the voltage super high, then the current will be super low. And then the energy losses will be very, very small. And that's actually what happens. That's why we say, oh, careful. This wire is a high tension line. High tension means high voltage. So there's a huge PD between these two lines, between this line and the ground. And that's why we say, don't touch it. This ensures that the current is very, very, very small and that we can transmit power across the country in a very cheap way. What happens then when this thing gets to our house? When this gets to our house at 40,000 volts, then you can't use a 40,000 volt hair dryer because that would not really dry your hair, that would burn your hair, right? So what you need to do is then you need to use another transformer, and then what you do is you decrease the voltage to the voltage that we normally use, which is 220 volts. So you come from 40,000 volts from your electricity transmission lines, and then once it reaches home, we use another transformer to make it a voltage that we can actually use at home. And that's how electricity transmission across the country works. You generate a certain voltage, you use transformers to up the voltage, lower the current. When we get home, use another transformer to make the voltage lower again so that we can use it at home and not get electrocuted and die. So that's why transformers are so useful and so important to your everyday life. Now what comes here is very theoretical, and there will be no problems you'll have to do with this. You just need to understand what I mean. And later on in class, I will just make you reread some stuff so that this sinks in, because it's quite a bit. But again, nothing too complicated. It's just remembering the theory. And this is about how we use electricity in our homes and how, the possible hazards that you can run into when you use it. And, the basic architecture of it all. So the idea is that at home, so we receive AC power from the company that gives it to us. And then we have two wires, okay? Now, one wire, which I'm going to depict in red, is called the live wire. And I'm going to make a little switch. And the thing about the live wire is that it's the wire that carries the potential. So this wire is a really high potential. Now, apart from this, we have another wire, which is called the neutral wire. And guess why it's called the neutral wire? Well, it's called the neutral wire because it's at zero potential, it's neutral. And what makes electricity go in our house is that there's a potential difference between these two. So if I connect something, it will be connected to both things, and then things will work. So these two wires are really inside the cable that leads to your appliance. They're not two different wires, like they're inside one cable that will lead to your hairdryer, whatever it is. Now, so let me just write the names here. We call this the live wire, some people call it the hot wire, and we call this the neutral, and some people call it the cold wire. Okay. Now, what happens here is that sometimes things malfunction. There's not enough resistance, for example, and this thing heats up. And what happens when this thing heats up? Well, what could happen, for example, is that it burns the insulation. And if it burns the insulation, then sparks could start flying around. And when that happens, you could start a fire. And that's not cool. So we need some way to make sure that this thing does not overheat. And the way we do this is using something called a fuse that we just represent like this. So just a little square on top of the wire. And you need to show the wire because otherwise it's a resistance. And the thing about the fuse is that it fuses. So it's made of some waxy material. And then when this gets too hot, it melts. it melts and it closes the circuit. So out. And then it closes the circuit, no more electricity goes through, prevents anything burning. So fuses are very important in order to ensure our safety, because without a fuse, what would happen is, things could overheat, then cause sparks, then cause a fire. Okay? Now, apart from this, some appliances will be connected to something called the earth wire. And I'm going to use another color for it. So let's just call it green. So there's another wire called the earth wire, and that's connected to the earth, because you can imagine the earth as being this huge reservoir of charge. You can just dump as much charge as you want on the earth and it will absorb it all. So every time that you connect anything that's charged into the earth, all the extra charge will go to the earth and the thing will remain neutral. And when do we use this? So for example, imagine that I'm using a metal kettle. So here's, you know what a kettle is, right? It's a water boiler, Wasser boiler. Okay, that looks like a tank, but it's a kettle. See, there's the smoke. So I'm using this kettle, and because it's connected to a live wire, it could be accumulating charge because it's metal. So if I have this on some plastic table or some wooden table that does not conduct electricity, the charge will just keep accumulating on this. And then if I touch it, I'm going to get electrocuted. And again, that's not fun. So what we do is we connect this kettle, apart from to these two wires, we connect it to our earth wire, so that any extra charge that starts accumulating here automatically goes to the earth, and then it's perfectly safe to touch. We don't, get electrocuted. Some appliances don't have an earth wire because they have something called double insulation, which basically means that they're made of plastic, and then therefore there's no charge that accumulates in them, and then you just don't need to concern yourself with that. So again, either you earth your appliances or you make sure that they're very well insulated so that electricity cannot go through. Now, what most houses actually have, well, not every house now has, is something called a circuit breaker, which is placed in a box. Now, I'm sure most of you have seen this in your houses. So, here's your neutral wire, here's your live wire, and there's a company fuse just in case things really, really go south. And then this goes to this box. And in this box, well, there's a switch for both. And then this continues because we really the neutral wire doesn't really need to do anything else. But this one is split into many. And each one has a different current. So this one is split into this, 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 this. And then for each one of these, we have this little switch. And what this switch does is, if there's too much current going through this wire, it just turns it off. I mean, I'm sure you've seen this at home. It looks something like this. So here's and then you have this little switch that goes like this. And then sometimes it will go off like this, and then you'll have to turn it back on. And when this happens, it's just because each one of these things has a limit. So for example, 15 amperes, or for example, 30 amperes. And then when the current goes over this limit, this switch automatically closes the current. And if we want to get it to work again, we just go and switch the switch back on. So again, this is a safety measure, and it's way better than a fuse, because fuses just fuse, and then you just need to change the fuse. Whereas this, just, click, and then all you need to do is unclick it. You don't need to change the fuse, you need to call an electrician, etc., etc., etc. I'm sure that, all of you guys have seen this box at your place where you can just turn the switches up and down. These things are called circuit breakers. And they're called circuit breakers because, guess why? They break the circuit. So again, if the current goes above the specified value, this goes off, breaks the circuit, and then nothing bad happens. We've already gone through some of the hazards that having electricity at home may bring, but I'm just going to comment on some others. So for example, I'm sure you've heard that if you're in the bathroom, so this is, toilet sink, a sink. it's dangerous to use electrical appliances. And you might be wondering why. Well, the reason is basically that there's water in it. And water, not distilled water, but the water that you get here, is a conductor. So if for whatever reason your appliances get soaked, then electricity may run through the water and then catch you, and then you'll get electrocuted and you could, get seriously hurt or die. So one possible hazard is damp conditions. We want to make sure that our electrical appliances are always dry, there's no water in them, to make sure that we don't get electrocuted. Now, another possible problem is overheating, and we already talked about this. So if we have, for example, a very long cable, these cables have quite a bit of resistance, so they tend to heat up, and then they get overheated, and then when they get overheated, they could start a fire and whatnot. Way to avoid this is, of course, using circuit breakers, fuses, and all that stuff. And finally, another thing that can happen is that for whatever reason, you have a cable and the insulation gets peeled off. So here's my insulation layer. For whatever reason, the mouse ate it. This gets peeled off. And then if the insulation is damaged, again, it's possible for electricity to jump from here to whoever is close to the cable, or for example, jump to the floor, to the curtains, start a fire. So again, it's very important to check our wires to make sure that the insulation is always correct in them. Otherwise, fire, electrocution, you name it. All right, so that's it. Let's see if we remember what we did. So describe the construction of basic transformers. Remember, iron core, 2 coils, and different number of coils in each one, because otherwise, why are you doing this? Recall and use the transformer equation. Remember that it was that the voltage in the output over the voltage in the input is the number of turns in the output over the number of turns in the input. Describe the use of transformers in transmission of electricity. Remember that we use them to increase the voltage so that the current decreases, so that it's cheaper to transport because there's no losses. Recall and use the transformer power equation. And then this one just said that the voltage in the output times the current in the output has to be equal to the voltage in the input times the current in the input. Now, demonstrate understanding of the use of fuses and common electrical hazards. So this is what we just did. Fuses, remember, are these things that we put in circuits to make sure they don't overheat. And finally, demonstrate understanding of the use of circuit breakers. That's where you have this little circuit breaker box, and then when the current goes above a certain value, the switch just goes off. That's pretty much it. And next day we have a lot of work to do. Again, the class is not going to be differentiated because there's lots of theory but very little practice, so it's really hard to have a difficulty curve. So this is basically about practicing and memorizing and making sure that we understand these things very well before we move on.